The upper and lower bound algorithms for the travelling salesperson problem can also be done in matrix form. We're going to look at that now. So we're going to use the nearest neighbour algorithm starting from node A but in matrix form. So this is the network we're going to use. The nearest neighbour algorithm starts very similarly to Prim's algorithm in matrix form, but there are some differences. We're going to start by circling the starting node, in this case A, and crossing off row A. We're then going to look down column A for the nearest neighbour, and we see that the nearest neighbour is C. So instead of adding this to a table, we're going to write it as a tour. So the first part of the tour will be A-C, and we're going to write the weight 1 just above the dash. Then in the same way as with Prim's, we're going to add node C by circling it at the top and crossing out its row. But the difference between this and Prim's algorithm is that with Prim's algorithm you would now look down column A and column C and choose the smallest arc. In this case we are only looking at the nearest neighbour from C, so we're only going to look down column C. And we can see that the smallest weight from C is C to F. So we're going to add C to F with a length of 4 to our tour. Add F by circling the top and crossing off the row. I'm going to continue like that. So we're going to look down column F now for the nearest neighbour. We see that the nearest neighbour to F is D, with a weight of 1. So add F to D to the tour. Add D as a node by circling it and cross out row D. We've now got two choices from D. We can either go to B or E. We're going to go to B because it's the nearest. So D to B has got a weight of 2. Add B and cross out the row. Then we're going to start from B, and the only place that's not been visited now is node E. So we're going to add edge BE. Circle E and cross it out. Now we've not finished yet because we are looking for a tour. We need to go back to the start. So now from E, we need to look down the column to find the distance back to A again. E back to A is then 4. So we've now found a tour. This will act as an upper bound, ACFDBEA. That tour has got a weight of 19. We're now going to look at the lower bound algorithm in matrix form. So you'll recall that the lower bound algorithm involves taking a node, deleting it, and finding the minimum spanning tree that connects all of the remaining nodes apart from the one that's deleted, and then adding the two arcs of lowest weight that come from the deleted node, and the sum of those arcs altogether will give us the lower bound. So we can do that in this case by first of all picking the two smallest arcs. We're going to choose node A. The two smallest arcs from node A are A to C and A to B. So we're going to use those in our final answer. We're then going to delete node A. Now the easiest way to do this is to rewrite the table with column A and row A missed out. I'm just going to shade those out there, but you may rewrite these in your calculation, so you rewrite the table. We're then going to find the minimum spanning tree using the nodes B, C, D, E and F. Since we are in matrix form, the easiest way to find a minimum spanning tree is to use Prim's algorithm. So you would use Prim's algorithm to find a minimum spanning tree for the remaining nodes. So Prim's algorithm gives us BD, assuming we started at B, then gives us DF, then gives us DE, and CF. So those are the 4 arcs that will make up the minimum spanning tree of the remaining vertices. That gives us a weight of 10. We can then add that weight to the two smallest arcs from A, which were AC and AB, giving us a total of 13. It's important that in your solution to this you write down all of the arcs that are included. So the nearest neighbour algorithm gave us an upper bound of 19. Remember that we can always improve on an upper bound by starting from different nodes, and the smaller the upper bound, the better. The lower bound algorithm has given us a lower bound of 13. Again, this may have been improved upon if we had tried deleting different nodes instead, and the higher the lower bound, the better. As it stands, we can say that the optimum TOR will be greater than or equal to 13 and less than or equal to 19. So pause the slide now and find an upper bound using the nearest neighbour algorithm, this time starting from node C. So we're going to start with node C, let's cross it off and look for the nearest neighbour. The nearest neighbour to C is A. That means that we can start our TOR with CA with a 1 above the dash. We're then going to add node A, so circle it and cross out the row. Find the nearest neighbour from A. The nearest neighbour to A is B, so we can add A to B to our TOR. We can also now circle B and cross off row B. Looking down the column now from B, we can see the nearest neighbour is D, so B to D is 2. We can now circle D as well and cross off row D. The nearest neighbour to D is now F, so D to F is added and we circle and cross off F. The nearest neighbour now from F is E. It's the only place we haven't visited so far, so F to E. And then finally we need to get from E back to C, and we can see that the distance from E to C is 5. So here we have now got an upper bound of 18. That is an improvement on the previous upper bound of 19, so we're going to use that. So pause the slide again, and this time do the lower bound algorithm to find a lower bound, but this time by deleting node D. So if node D is going to be the node that we delete, we first of all need to identify the two shortest arcs from D. They are D to F with a weight of 1 and D to B with a weight of 2. Now that we've found those, we can now delete D. Remember that this is done easiest by redrawing the table but missing out row D and column D. We can now do Prim's algorithm. If we start from A, Prim's algorithm will first of all give us AC. It will then give us AB. Then it gives us AE. And finally CF. So the minimum spanning tree with the remaining nodes adds up to 11. If we then add together the two values of the arcs from D, we end up with 14 as our lower bound. So this is an improvement on the previous lower bound. The previous lower bound we had was 13, so the higher the lower bound the better. So the previous upper bound was 19, but we managed to improve upon that with 18. The previous lower bound was 13, and we managed to improve upon that with 14. So our new TOR can be narrowed to being greater than or equal to 14, but less than or equal to 18. Now complete exercise 2.4 on page 39.